Okay, let's begin. So, let's start by going over a couple problems in homework 1. Someone had trouble with these two, so I thought I'd go over them. The first one is drawing Venn diagrams. Like I said, they are not good enough for proofs, but they are good enough to give you some sort of intuition about where you might want to take a proof. So, suppose U is some universal set, A and B are subsets of U. How do you draw Venn diagrams for A union B? The complement of A union B. Draw two circles. Draw them overlapping, but they don't necessarily have to have elements in common. This could actually be empty here. So what would A union B actually look like? You shade both circles, right? So what do you think the complement of that looks like? Everything else, right? Remember, it's the things that are in the universal set that are not in the set being considered. So A union B is actually both circles combined together. You shade them all. The complement is just everything else. What about A complement intersected with B complement? Well, A complement is everything outside of A, including this part here in B. But B complement is everything outside of B. And since you want the intersection, you will actually end up being the same thing. Are there any questions on why that is? There is that. Sure. Because if I'm graphing A complement, it's everything here. If I'm graphing B complement, it's everything here. This is A and B. And so the intersection, the parts that's shaded in both, is actually just the outside. Because this is shaded in this one, but it's not shaded in that one, and this is shaded in this one, but it's not shaded in that one, therefore it's not an intersection. It ends up being everything outside. What about A intersected with B, and then you take the complement of that? A, B. Okay, so what's the intersection of A and B? It will just be the guy in the middle here, the overlap. So you can take the complement, pretty much get everything outside of that. Similarly here. Think of A complement, which is everything outside A, and B complement, which is everything outside B. And if you take the union of those, you actually end up with the same thing. And I believe there was a part B to this question, where it says, what can you conclude? Well, from the pictures, it would seem that A union B complement is actually the same as A complement intersect B complement, and A intersect B complement is the same as A complement union B complement. Pictures is not enough for proof, but based on what you've done, that would be a guess of yours. These are actually called De Morgan's laws, and you can actually prove them, but you wouldn't prove them with a picture. We'll talk about how you prove them later when we talk about proofs. So chapter 3, we can come back and see how you actually prove those. Moving on to problem 41. Does anyone have an example?
The integral from 0 to 1 over n.
That works. There was a similar example example in the textbook, in one of the examples where it went from minus 1 over n to 1 over n, and you see that those closed in from minus 1 and 1 all the way down to 0. So you sort of use the same principle here. Notice that this is going from n equals 1, so you see when n equals 1, you get the interval 0 to 1, right? And that will actually be the largest interval, because as your n increases, the interval actually gets smaller. So this will be the union. Everyone will be that or smaller. However, 1 over n, as n increases to infinity, the interval starts getting smaller and it approaches 0. It turns out that the only guy that was in every interval will be the number 0. So that was the idea there. What about this one? What would you think your an is?
All x such that x is a number of integers from x between negative and n.
Yes, we interval from negative n.
Okay, so you want to be like x such that x is an integer and x is between
Negative n.
minus n to n.
Yeah.
Okay. Sort of work to see the n over there, but yeah, that's fine. I could also do something like to flesh that out. What you're really saying is like minus n. Minus n minus 1, minus n minus 2. Stop. Also, that could also work. Yeah, well, absolute values, so you can write this another way with absolute values. But yeah, any of those will work. So basically, you always want your set to keep these guys, the minus 1, 0, and 1, and then let your n count up all the other integers. And this will always be in every set, but the n, well, here you can say this is for when and you could just make it count plus 1 or something. So in that case, all your sets have 5 elements in them, and their union will actually be the entire set of integers. What about the question on the quiz that I gave you? With the index collection of sets. Where I said I is just this interval of real numbers. So it's the half real line. And I said R is an element in I. And I defined these 3 sets, AR, BR, CR. This is a set of all coordinates in the 2D plane such that x squared plus y squared equals r squared. This is the set of all coordinates in the 2D plane such that x squared plus y squared less than or equal to r squared, and this is the set of x, y. And I actually to find three things: the union of all R and I of A R, the intersection of R and I of A R, What were the answers?
R, A, the first part is R2, like all of this set to a point in R2.
Yes, in fact, the union of all points, such points in A is in fact all of R2. What is the intersection?
The null set, or not zero? No, sorry, null set.
It's actually the empty set.
Yeah.
Okay. How do you know that? How did you figure that out? The guys in A's are just what? Circles centered at the origin, right? So when R is 0, you have this circle. Let's say R is 1, you'd have that circle. Let's say R is 2, you'd have that circle. This is 1, 2, so on and so forth. Right? And they're just branching out. Except your R can be any real number. So it's actually all possible circles of all possible radii. Eventually, this will all get filled in, right? So if you take them all together, you literally will fill in all the gaps because your radius is every real number along the real line. So you'll eventually fill in all the gaps if you take the union. However, you can see once your radius is not the same, your circles, your points here will never intersect with any other points on any other circle. And so that's why the intersection is empty. However, in B, the situation is slightly different. So R equals 0 would be here. If I say R equals 1, it not only takes that circle, but it fills in everything on the inside. R equals 2 would take that circle, but it would fill in everything on the inside. And so on and so forth. So we're getting larger circles, but now we're filling in everything. Right? So what's the union?
R2.
Again, it's R2. What's the intersection?
0.
Will it be the origin? That will be the only point. The origin will be the intersection of everyone. Everyone will have the center 0, 0, but not everyone will have every other point. So in C, now we're bigger than some circle, right? So we take some circle of radius r, and we basically fill in everything outside that circle. Starting from r equals 0, going outward. So what's the union of all such circles?
All numbers except 0, because it's not including.
Right, it's not including r, so it's literally r2 minus 0, 0. Right? Because even when your r is 0, you don't take that point, you take all points outside of it. So the origin is a whole for all such circles. And if I had put a greater than or equal to here, it would be all of r. What about the intersection? What is the set of points that are in all such possible sets?
Yeah,
It's again the empty set. Okay. And if you started to draw these pictures, you would see that that's probably the best way to go about it. Anyway, let's move on. I'd love to get through chapter 2 and into chapter 3 where we start to have a little bit of fun, but I know that's unrealistic. We have to be somewhat thorough. But just so you know, in general, even though I'm trying to be thorough. There will be a lot of things that I miss out just because. I'd like to be able to spend more time on things that are more important. These first few chapters are important, but you're not going to really see them. Things in this way all the time. It's sort of a very lower level. And it's also sort of foreshadowing what's coming in your higher level math classes. You see, like in the lower level classes, like, you know, Calc 1 or Calc 2 or something like that, it's very easy to be comprehensive. Like, you know, I can tell you, okay, so this is a quadratic, and if you want to find the roots, this is how you do it. If you can factor it, you can FOIL it, you can factor it, you can find the roots that way. If that doesn't work, use a quadratic formula. And literally, any quadratic you ever encounter, you can use one of those methods. It's comprehensive. I can just tell you like that, and you know everything. The higher you get, the less that is true. I can tell you tons of stuff, and there will still be some problem out there that you're going to approach it, and you're like, I don't know. I don't know what to do, right? So it's like, there's no like hard and fast rule to get something done. You have to really be creative, and you have to sort of mix and match all these different things that you know about and try to order them in a certain way that it will solve this problem. And it's just, there are way too many variations for me to anticipate. So I couldn't tell you everything even if I wanted to, and I tried. So there's no point. I'm just trying to give you the fundamental, essential stuff that you need to know. The kind of stuff that sort of becomes ingrained in you when you're a math person, when you forget all the technicalities and you're actually in the real world solving problems. The things that the kind of knowledge that you pull on, that's sort of the knowledge that I'm trying to give you, sort of. So, hopefully it's comprehensive enough, but if not, like I said, I think the textbook is great. You read the textbook, it should fill in any of the gaps, but for now we're just going to try to move on with haste and some sort of comprehension. So last time we started talking about statements, which were declarative statements that can be true or false, but not both. We mentioned open statements. We talked a little bit about the truth table. We'll do a lot more with truth tables today. I gave you the definition of the negation, and I showed you a truth table with P and not P. Okay, so let us continue. Oh, by the way, both the lectures are actually up on the YouTube already. If you go to my website, there is going to be a link that says, hey, click here for the YouTube videos, and you can see them. Also, the answers for quiz 1 are already up. I didn't grade all the quizzes, but I will grade them and give them back. So Monday, I'll give you back the 2 quizzes that we've done. And the answers for the quiz is already on my webpage. So, chapter 2, we are going to continue with, what did I want to talk about? Disjunctions and conjunctions. Let's start with the disjunction. For statements P and Q, right? Declarative sentences that can be true or false, but not both. The disjunction of P and Q is the statement P or Q. And this is an inclusive or. Right? Meaning either the statement P is true, or the statement Q is true, or both are true. Right? And it's denoted P, V, Q. Right? So that little V means or, right? So this means P or Q. That's how you would read it. It is defined the truth table. So remember, truth table is just a table that arranges all the truth values of our statements, and we can actually make a conclusion about some other statements created from those two original statements. So at P and Q, and I'm looking at P or Q. So first thing we want to do is figure out what are all possible combinations of truth values for P and Q. We'll sort of use a binary system to set these up, meaning here you skip every one time between true and false. Every time you step over, you skip every 2 times. Right? If there was a third one, you'd skip every 4 times, then every 8 times, then every 16 times, and so on and so forth. It actually bumps up by 2. So you skip every 2 to the 0 times, here every 2 to the 1 times. In the next one, you skip every 2 to the 2 times, and so on and so forth. So we skip here every 1 from true and false, skip here every 2 between trues and false. When we do things with 3 statements, you'll see I'll skip every 4. So with 3 statements, there will be 8 total possibilities for arrangement of truth values. For 2 statements, there are 4. They can either both be true, this one is true, or that one's false, this one's true, or that one's false, or they're both false. Right? Now, to define P or Q, the inclusive or, we're talking about when one or the other is true. So, if P and Q are both true, what is P or Q, the truth value? Well, it had to be true, because both are true. What about here? It's also true, because P is true, Q is false, but it doesn't matter, it's an or, right? Here, Q is true, P is false, doesn't matter, it's an or. So once one of them are true, we're good. Both are false is the only situation where we have a false. Right? So this is sort of giving you the possible arrangements of the truth values for the statement P or Q, depending on the 2 separate statements. So these are 2 separate statements on their own. This is a new statement I made by combining 2 statements with an or, and this is how the truth values will behave, depending on the truth values of the previous 2 statements. There is also the conjunction, which is basically and, right? For statements P and Q, the conjunction of P and Q is the statement P and Q. P and Q. It's denoted P caret Q. Okay. It's literally read P and Q. Okay. It's defined by the truth table. Well, what is this? How do you think it will be defined?
True, false, false.
Right. They both have to be true at the same time. Right? So it will only be true in the case where P and Q are actually true. That's when it's true. If one or both are false, it's false. That is called the conjunction, and that's how it behaves. And again, like I said, P and Q, you can think of these as statements. I can say, 3 is prime and x squared plus 1 is always greater than or equal to 0 for all x, or it could be whatever, right? Whatever statements I want to make. Whatever is a declarative statement that we can determine to be true or false. The next important kind of statement is called the implication. Triple underline. It's a super important kind of statement. So, statements, P and Q, you define P implies Q. It is denoted P, and you put this arrow in Q. And there are many things that let me do the truth table and then talk about equivalence. It is defined by the truth table Does anyone actually know how it's defined?
True, false, true.
True, false, true, true. Okay. So let's talk a little bit more about the implication because it's very important. Talk about all the sentences that are equivalent to P plus Q. So, very common way, common way to express it in math terms is if P, then Q. There are other ways. So, for example, we can say P only if Q. You can say P is sufficient for Q. You can say Q is necessary for P. You can say Q if P that's all the ways I have written. There are probably a few others. But they'll probably make more sense when I talk about quantified statements. Okay, so the first one, which is the most common one, should sort of give you the idea of why this is such an important statement. There are so many statements that have this form. Like not only in math, but in like everyday life. So in like math, you'd say things like, you'd see a theorem in your talk book saying something like, well, if a function is differentiable, then it's continuous, right? Or in real life, you might hear someone say, like a politician, if you elect me for president, I will lower taxes, right? Like people make statements like this all the time, right? You know, you do this, if you scratch my back, I'll scratch your back, right? Every time someone makes a promise to you, they're sort of telling you an implication, right? It's all over the place. Every contract is actually an implication, which it's sort of the way that people usually explain this to make that truth table make sense. Because one thing you'll note from the truth table is a false statement implies anything. Right? So once you start telling me a false statement, then it doesn't matter what else you say, A, I have to consider that as a true statement, which some people find very odd. One way to think of this, one way to think of this is a contract. Right? So let me say something like, example. If you elect me president, I will lower taxes. Right? And if I ask you the question, when is this false? When will that be a false statement? When will you be able to say the person who made that statement told me a lie?
You elect them or don't elect them.
If you elect.
If we actually elect him president,
Yeah.
and he doesn't lower taxes, then we will say, you're a liar, right? You didn't tell us the truth. You told us a false statement, right? So if you look at this as the P, and I will lower taxes as the Q, then if your P is true but your Q is false, then you're like, it's false. Like you said if you did this, this would happen. If this happens, that will happen. That's what you said. But no, it's false. Now, let's look at the situation where we don't elect him president. So now consider the two cases. Maybe he still goes on to lower taxes somehow as a governor or some other lower office. Or he doesn't lower taxes, right? In either case, could he have said he made a false statement? No, because if you didn't make him president, he is free from all obligation. He can lower taxes or not, and it's up to him. It's not a lie, right? And because there's only two possibilities for a statement, you can't really say he made a false statement, so it must be true, because that's what a statement is. It has to be true or false, but not both. So if you can know it's not false, it has to be true, right? So that's sort of why it will be true in all cases, even when the implication is false. The only time it's false is when this is true, but that is false. That's the only time you'd be able to say, you told me a lie. So I could say something like, if pigs fly, I'll give you a name in the class. Right? Or if you study hard, then you will pass. These are all implications, but you can clearly see there are times when the first part can be false, yet overall the thing is true. Right? So I know students usually have a lot of problems with this, but that's probably the best way to think about it for this truth table to make sense. It's the only time it's false is when P is true and Q is false. All other cases it's true. In particular, when the first statement is a false statement, the overall statement is considered true from a logical standpoint. Sometimes that might not make sense to you, but logically speaking, you can't actually prove the statement is false in those situations, so it has to be true. Because, well, you can prove it's not false. So, when we get to trivial and vacuous proofs, you'll see that idea being applied. But this is, like I said, a very, very important kind of statements, and a lot of the statements that we want to prove in the future can be written in this form. I had some more notes on it. This is not really important, but whatever. In P implies Q. P is called, they might call it the hypothesis. They also might call it the the word I. In the statement P implies Q, P is called the hypothesis or the antecedent or it's probably another word for it, I don't particularly. Premise. Premise. Q is called the conclusion or the consequent. Just in case you're reading that somewhere, or I might say that when I'm talking to you, that's what I'm talking about. So I say, oh, the consequent is blah, blah, blah. You should know that I'm talking about a statement, P implies Q, and I'm talking about the second statement. Okay. So, let's look at another kind of statement. Biconditional, or it's sometimes called bi-implication. For statements P and Q, the biconditional P and Q is the statement P implies Q and Q implies P. So what happens is when you have an implication going in both directions, you call that a bi-implication or a biconditional. It is denoted P, and you draw an arrow going both ways Q, right? Which means P implies Q, but also Q implies P. They both point to each other, right? So if P then Q, and also if Q then P, you get the biconditional. It is defined by the truth table. False statement implies anything, remember that. With a false statement, I can say whatever. Okay. The truth table for biconditional. P. P. What do you think it would look like? True, false, false, true. Is that your guess?
False.
How can you check it? How would you check it? What do we say this means?
That means
Implication is going both ways, right? So if you drew the truth table, and I talked about P, Q, and I looked at P implies Q, and I looked at Q implies P, and then I looked at P implies Q, and Q implies P. Right. So we looked at P implies Q. We know the only time it's false is when P is true and Q is false, and it's true in every other case. Q implies P. It's only false if Q is true and P is false, and it's true in every other case. Right. So now if I look at both of these, this and this, it will be true here, it will be false here, it will be false here, and it will be true here. So that is the correct truth table. So again, you can always break statements up, take them piece by piece, and verify the truth of each statement piece by piece, and then combine them all to get the truth table of the entire thing. So yes, this is the truth table for the biconditional. We have, again, other phrases. Ways to phrase the biconditional. So P implies if and only if Q is one way. So the common way is to say P if and only if Q. Sometimes you write a shorthand, you write two F's. That's what it means. So if you see me write that, it's not a typo. I know how to spell the word if. It's actually on purpose. So if I say two F's, I'm talking about a biconditional. You can also say P, and this is one of the important phrases, this is one you should remember, is equivalent to Q. Right? Equivalency is going to be an important thing, we're going to get that to later. We can also say something like P is necessary and sufficient. For Q. Right? All these mean the same thing, right? So if there's ever a case where in English you phrase it in one of these ways, in math, this is how you think about it. But notice why we can say it's equivalent is because it sort of tells you when P and Q actually behave the same way. When they're both true, it's true. And if they're both false, it's true. If they do different things, it's false, right? So this is sort of saying they're sort of equivalent. Whenever things behave the same way, this guy is going to give you a truth value, right? And if they behave differently, it won't give you the truth value, which means the bi-implication in some sense is a way to test equivalencies. It will tell you when two different statements behave in exactly the same way from a logical standpoint, which is going to be very important very soon. The idea behind this is the following. Well, the reason why it's important is the following. Is sometimes you'll want to prove a statement, but attacking it with that statement is sort of complicated. You don't really know how to formulate an argument or what angle to approach it. But if you can rephrase the statement in a way where it's more mathematically palatable, that would be good. You need to know if the statement you're rephrasing it as is actually equivalent to the original statement, meaning it'll be true when the original is true, it'll be false when the original is false, and that's the only time when a proof of another statement will be accepted, right? It has to be equivalent, and you will need to check it with equivalencies. So we'll talk a little bit more about that soon. We can write in this case right, like an equal sign but with 3 bars, right? This is actually the symbol for equivalence.
That's the same as a condition. So those 3 bars can mean the same thing as double arrow.
Yep. But typically we'll write it this way unless we specifically want to emphasize this. You'll usually not write it when you just have 2 statements, but when you have compound statements, which we will get to, it will be typical to write this. And we'll get to some of those. Let's talk about tautologies and contradictions. Two very important ideas again. Definition. tautology is a statement that is always true. No matter what. A contradiction is a statement that is always false. Let's do some examples. Let's look at the statement P and not P. This is a contradiction. I am Batman and I am not Batman. Right? Can't be a true statement. Right? So if I look at P, not P, and P and not P, right? So remember how we set this up. It was, this could be true or false. This is going to be the opposite, false or true. And that's all the possible arrangements of the truth values of these guys. Because if this is that, then if you do the and, you will realize that this is always false. So that means this guy is a contradiction. It's false in every instance, right? Always false. You call it a contradiction, right? By always, I mean in every instance for every distribution of truth values. Of the statements that make it up. So you have a statement, and no matter what the truth values of the pieces are, you always get something false. You call it a contradiction. If you always get something true, you call it a tautology. And
If you change it,
let's do. Yes, that is. I didn't write that example, but that's actually a good example to write down. Because that is something that you'll see me use in proof sometimes. Right? If you have P or not P, then you have P, not P, P or not P. This would be true, false, false, true. Then this will actually be true and true. This would be a tautology. Right. Later on, you're going to see us do proofs like that sometimes. We're going to start off a proof saying something like, well, either it is or it isn't. Right? And I can say that because such a statement is true. We'll see examples of that later on. Another tautology. Let's look at this statement. P implies P or Q. What do you think that is?
Tautology.
So if we look at these statements, how do you sort of verify what they are?
Write down the truth values.
Write down the truth values, so you can do a truth table, P and Q. True, false, true, false. So what are the things we want? I probably want to do P or Q. And then I can do P implies P or Q, because then I'll have all the pieces. So P or Q would look like what? Well, true. And so now P implies P or Q. Well, true implies true is true. True implies true is true. False implies anything. Right? So once the first statement is false, once your antecedent is false, the overall statement is true. So this is a tautology. Do a similar thing here. I can do P, Q, not Q. And I can do P and not Q. And I can do P and Q. And then I can do P and not Q. And P and Q.
Being mathematical, that makes the whole statement false. So maybe we need to check for Q and RQ and P and Q and P is false. So just the first two.
For which one?
For P being true. Because if P is false, it's mathematical, makes the whole statement false.
Right, so you're saying P is false here, this will be false.
Yeah.
And if that's false, then this is false. Yeah. So you could look at that. So you know that in these statements you'll have false. So what about if P is true?
Well, not Q is false, so it's going to be false.
Either Q or not Q is going to be false, so it's going to be done.
Okay. So this will be
False.
false. This will be true. This will be
True. False. False. False.
So sometimes you didn't, yeah, these you didn't matter at all. And so we have, again, a contradiction. Yeah. She stole my ice cream and kicked my dog, and she stole my ice cream but didn't kick my dog. She's a horrible person, I believe, but I just lied. So I guess. What else do we want to say? Well, expressions like the above, meaning we're talking about things like P implies P or Q, and P and not P, etc. are called compound statements. They are logical statements combined using things like and, or, implication, bi-implication, and these guys are called logical connectives because they're used to connect logical statements. You mean the statement P if and only if Q?
Yeah, but it.
That is a compound statement.
Compound.
Yes. Anytime you combine two statements using any of these symbols, it's called a compound statement. And as you can see, how we deal with compound statements is essentially divide and conquer. You break it up into pieces where you don't have the connectives, and then you just deal with it piece by piece. Which is going to be a common thing. What else do I want to talk about? So that's logical equivalence. So let's do an example. Show that P for Q and R is logically equivalent to the statement P or Q and P for R. We started to show this using the truth table to prove that the truth values are the same in every instance. We have three statements here, and I'm making the statement P is true or both Q and R are true. So start with P, Q, R. What does the distribution of truth values look like here?
4 truths and 2 but then alternating.
You're starting from here, so we have 4 truths, 4 false,
Then
and 2 truths, 2 false, 2 truths, 2 false. And then true, false, true, false, true, false, true, false. That's all possible arrangements of the true, false truth values for 3 statements. Alright, so what do we want Maybe having a Q and an R would be good. Then I will put the first statement that I want, P or Q. We must have a P or a Q, and a P or an R, and then I connect them, P or Q, and P or R. So, Q or R, Q and R. What is that here? True? False. Okay, now what if I say this or that? Well, it's true for the first four because these are true. And then here it's true because this is true. It's false, false, false. Should have done that in black. Whatever. Okay, so P or Q, meaning I'm looking at these two. The first four are going to be true because P is true. The last four, it's true in the first two but false in the second. If I look at P or R, looking at these, it's true for the first four because P is true. For the last P, it's true, false, true. And so now I'm doing AND for these two columns. So it's going to be true, 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 false, false, false. And then what you do is you compare these two columns here, which are the statements in question. And you'll see they give you true all the same times and they give you false all the same times. These are equivalent. In other words, from a logical standpoint, making this statement with these three statements is exactly the same as making that statement with the three statements. Right? And depending on the situation, it might be easier to prove one as opposed to the other. So proving this is difficult, you could rephrase it as that and prove that, or vice versa. They are actually the same thing. Okay, so we won't finish. We'll probably just stop there. But the good news is next time we'll definitely get to chapter 3. I'm very sure. This is where the fun starts. We'll actually start proving stuff and learn those techniques. So we'll stop there. I'll see you guys on Monday. I'll give you back your physics on that day as well. Remember chapter 1 homework?